Hi again and welcome to a new lecture in which we will do a second example related to stress blocks. So in this example, we will have the cross-section of what is called a non-symmetric I-beam. So it's an I-beam because it resembles the capital letter I, and non-symmetric because, as you can see, the top horizontal element, which is called the top flange, is wider than the bottom flange, so 160 millimeters wide, and the bottom flange, you will see, is less, only 130 millimeters wide. And not only that, but the thickness of the top flange is 18 millimeters, and it's also larger than the thickness of the bottom flange, which is 15 millimeters. The vertical part in between the flanges is called the web, and the height of the web is 307 millimeters. The thickness of the web is 10 millimeters. So this is the cross-section of, for example, a member, maybe a beam. And if we now to look sideways at a point along the member where this section was cut, and we draw now the left-hand side free body diagram. Here you can see the member here, the side of the member, and the stress block at the top acting on the face of the member, actually on the face of the cut of the member, is a compression stress block with a maximum stress intensity of 114 megapascals. And in red you can see the tension stress block at the bottom of the section with a maximum stress intensity of 141 megapascals. The neutral axis, where the stresses are zero, is located 188 millimeters from the bottom of the section and 152 millimeters from the top of the section. And again, this is a beam that we're told is in pure bending. So the total force normal to the cross section is zero, or in other words, the axial force, the net axial force in this beam is zero. We have to determine, firstly, the magnitude of the total compression force. So in other words, we need to determine the volume of the compression stress block, the blue one. Now, it might look simple because it looks like a triangular wedge-shaped stress block. But if you look carefully, this stress block acts partly on the web of the section and partly on the flange of the section. So this stress block has two different widths. So therefore, we have to calculate this separately for each of the two widths. We can use similar triangles to calculate the magnitude of the stress intensity at the interface between the flange and the web, and that will be 100.5 megapascals. So now we have defined the two stress blocks, the one acting across the flange at the top, it's a trapezoidal stress block, and the one acting across the web, which is a triangular stress block. So let's start with the top component that acts across the flange. So the total force corresponding to that is equal to the area of the trapezoid that we can see in the diagram. So 114 plus 100.5 megapascals divided by 2 multiplied by the depth of the trapezoid, 18 millimeters, and then multiplied by the width perpendicular to the side view of the flange, which is 160 millimeters. So don't forget about the third dimension, because even though we represent these in 2 dimensions here, these stress blocks are actually 3-dimensional stress blocks. Now, if we go down a little bit, we can determine the force in compression for the part of the web that is in compression, which is narrower. So that would be the volume of the triangular stress block. So in this case is the area of the triangle that we can see multiplied by the width of the stress block, which is actually the width of the web, or 10 millimeters. So if we do that, we will get a total of 67.335 kilonewtons, and the total compression force acting on this section will be the sum of the two. So 308.88 plus 67.335 gives us a total of 376.2 kilonewtons in compression. And this will be the answer to the first question in this problem. Now there's a second question for the same problem, which requires us to determine the magnitude of the internal bending moment. So what do we do in order to find that? Well, we need to find the location of the compression force, or forces, because this is a composite stress block in compression, and then we would have to do the same for the tension stress block, which is also a composite stress block. Find the magnitude of all these forces and their location, and then summing the forces, say about the neutral axis. Having said that, let's look at the part of the beam in compression. So I'm going to represent here only the stress blocks which are above the neutral axis, so the part in compression. So the overall stress block looks like a big triangle, like so. But again, don't forget that the top part, 18 millimeters, act on the part that is in compression across the flange, and the bottom part, 130 millimeters, acts across the web, which is 10 millimeters wide. So let's show these with colors. So the green colored here stress block acts across the web. It's the narrow one, and it has a total compression force resultant, say C1, that we've calculated before. We know its magnitude is 67.34 kilonewtons, acting at now 2/3 of 134 millimeters, that is 89.33 millimeters from the neutral axis. The top part of this stress block, the trapezoidal part, acts across the flange, which is wider. And since we don't know exactly the location of the trapezoid, we can divide this, we can split this stress block into a constant rectangular stress block having a magnitude of 100.5 megapascals, and then we can determine the total compression force corresponding to this stress block, C2, equals to the area of the stress block multiplied by the width, which, remember, is the width of the flange, that is 160 millimeters. So that would amount to a total of 289.4 kilonewtons for C2. And C2 will be located at a distance of 134 millimeters plus half of 18 millimeters. So that's a total of 143 millimeters. Then we also have a little triangular stress block, which was part of the original trapezoid, with a maximum stress intensity of 13.5 megapascals and an equivalent compression force C3 equal to the area of the triangular stress block multiplied again by the width of the flange, because it's acting on the flange, so 160 millimeters, would give us a total for C3 of 19.4 kilonewtons. And C3 would be located at 134 millimeters plus 2/3 of the thickness of the flange. So that would be a total of 146 millimeters measured again from the neutral axis. So we know all these three forces that together make the total compression force. Now we can calculate the moment of the compression stress block about the neutral axis by summing the forces of all these, by summing the moments of all these forces with regard to the neutral axis. So 67.34 kilonewtons times 89.33 millimeters, or 0.0893 meters, plus C2 multiplied by 0.143 meters plus C3 multiplied by 0.146 meters will give us a total moment for the compression stress block of 50.2 kilonewton meters, rotating, of course, counterclockwise. Now, we also need to calculate the moment of the tension stress block about the neutral axis. And in order to do that, I will let you do this as a homework, but the calculations would be similar as for the compression force. But now we have to go below the neutral axis, where the beam is in tension. And again, we will have another big triangular stress block in tension this time, part of it acting on the narrow web of the section and part of it acting on the wider flange part component of the section. So please do this on your own as an exercise. The only thing I will tell you is that the result that you should get for the moment due to the tension stress block with respect to the neutral axis has a magnitude of 60.6 kilonewton meters, and this will also rotate counterclockwise around the neutral axis. So both moments due to C and T rotate counterclockwise, so the total moment across the section due to these forces will be equal to the sum of these moments, so produced by C and T, so to a total of 110.8 kilonewton meters. So you have to be careful, as you can see, with regard to the width of the section across which the stress block acts. Now finally, there's one more question which requires you to calculate the tension force acting on the bottom flange of the beam, or in other words, the tension force corresponding to the stress block that developed across the flange, the bottom flange of the beam. So now if we represent the tension stress block below the neutral axis, which is the part in tension, again, like before, we have part of the stress block acting on the narrower web and part of the stress block acting on the wider flange. So the depth of the former is 173 millimeters, the depth of the latter is 15 millimeters. And of course we need to determine the total tension force corresponding to this stress block hatched in purple at the bottom, which is a composite stress block. We can divide it as we did before at the top into a uniform stress block and calculate a total tension force for that, plus a triangular stress block and again calculate the total tension force for that and add these together and obtain our result. Or maybe we can find a slightly simpler solution if we remember that this beam, this member, is in pure bending. So in other words, there is no axial force across the section. So then the total compression force must equal to the total tension force in this case. So in other words, if we then calculate T3, which is the tension force corresponding to the stress block acting across the web, which is a simpler triangular stress block, it's not a composite stress block, and by subtracting this one from the total compression force that we calculated in the previous steps, then we can determine the difference, which is exactly the total tension force acting on the bottom flange of the beam. So just in preparation, I've calculated here the magnitude of the stress at the interface between the flange and the web. So that tensile stress is 129.8 megapascals. And then we can easily calculate the total tension force corresponding to the stress block, equal to 112.3 kilonewtons. And please don't forget that this stress block acts across the web, which is only 10 millimeters thick. And now, finally, as mentioned, we can calculate the tension force acting on the bottom flange of the beam by subtracting T3 from the total C, and the final result will be 263.9 kilonewtons. So this would be, again, another typical question related to stress block. I would like to thank you very much for watching this lecture, and I look forward to seeing you at the next one.